So now we get into the power factor. And as I promised you before, I want to actually now discuss it very, very carefully. And please keep in mind what we want to do, what we want to assure when we design electronic circuit in AC, not in DC, only in AC, is to minimize the power factor, meaning to minimize the angle between the true power, effective, real, resistive, ideally, and the apparent power, which is the total. So if the angle will be low, the total that will go to the load will be exactly what the source generates, effectively, 100%. Cosine of 0 degrees is 1. So here we have the equations of every single pan of this triangle. And the Q is vertically, Q is the reactive. And it's equivalent to the apparent times the sine of the angle. The effective is the effective, apparent is the apparent is the total, and if we multiply it by the cosine, we'll get the effective. So the effective is always less than the apparent one, always less than the maximum, and the difference is loss. On the right hand side, we can see the formula, how we can calculate the power factor. And you can see the components of in this formula: kilowatts, kilovar. The less the kilovar, the higher the power factor. The higher the power factor because the angle is lower. We are in the cosine. And this is to summarize the power triangle. All the different equations, all the different formulas, you can look at this and you can plug numbers into it and get and find what you want. Same triangular, resistive purely is in kilowatts. It's real or true power. It's measured in watts. The apparent one, which is the total one, S, is measured in VA, voltage time current, but it's kVA. And the reactive, the Q, which can be a combination of the capacitive and the inductive, I remember you, is also measured in kilovar. And the power factor, the cosine of the angle, is the kilowatt divided by the kVA. And that number we want to bring up all the way up to 1, ideally. And just kind of an analogic time of presentation, we can look at the reactive power as the foam on top of the glass of beer. The beer itself is the real power. The apparent power is the total amount of liquid and foam that I have in the glass. And the reactive power is only that foam. But that foam avoids having full glass of beer. Now let's look at the improvement of the power factor. I mention again, and I put an emphasis on the importance to improve the power factor / improving the efficiency, reducing the losses. And we deal only in AC, as it's written here. Now there is a difference between apparent power and actually consumed power, effective power, due to the shift of voltage and current waveforms. Phase shift, we discussed that. By increasing the rate of effective power, power factor is equal to effective divided by apparent. Power loss can be reduced. So if we look now at the two graphs, we easily can see that if we bring the two waveforms together to be synchronized, to be in same phase, the voltage and the current, then the multiplication of them will be always positive and all the power will go out. So less power loss is when we have no phase shift or minimum phase shift. More power loss is when we have a phase shift and the loss is getting bigger when the phase shift is bigger. And why active power is important? Again, just to repeat it. So summarize the reactive and active, resistive versus reactive, which is inductive and capacitive. Where there is no phase shift, the product of current I and voltage A is an oscillating, yes, always positive output, pure active power. We can see it, the gray areas. Why power is important? Look at the picture on the right. The components of the power below, underneath the x-axis, is the power that goes back, like we said before. Here is being demonstrated fantastically. Supplied back power is the picture on the right, and consumed power is the picture on the left. The picture on the left, all the power is above zero. It's only going one direction, positive, from the source to the load. Benefits of high power factor. The benefits, by the way, is divided into two, for customers and for the utility companies. Because the utility company is basically generating the electricity for us. We, the customers, we actually consume it and use it. So there is a benefit for us if we improve the power factor at home, and there's a benefit for the utility company if they improve the power factor at their facility. Let's go. The benefit is, if we have a better power factor, it will reduce the effect of harmonics, which is basically electrical noise that may interfere with operations of computers, receivers, or sensitive equipment with your site. It will reduce potential for power quality problem. It might be that the sine wave itself will be distorted, because as current going in and current going out and there's a phase shift, it might distort the sine wave. And what we want to get from the electricity, from the utility company, is a pure, nice sine wave. Have a certain frequency, have a certain amplitude, certain cycle time. I don't want anything which is disturbed, which is not smooth, nicely sine wave. A better power factor also reduced power fluctuations caused by switching on heavy loads with your installation. So if I connect a heavy load and disconnect a heavy load, and this particular load has inductance, capacitance, and resistance, a combination of all the three, it will generate power fluctuations. And my television at home does not want to get power fluctuations. It needs to get the power that needs to get based on the technical specification. I don't need technical voltage fluctuations on my appliances at home. If the effective output will be identical, theoretically and ideally, will be identical to the apparent output, that means all what the utility company will do, that's what I will get. And when they generate pure sine wave, I will get the pure sine wave, no matter if I switch on or switch off a load. Once I have reactive, which is capacitive and inductive, there are all kinds of side effects because they are not pure. So voltage will fluctuate. Just a note, interesting note. Many utility companies provide incentives to consumers to improve their own power factor and thereby reduce their demand for electric current. Because the efficiency will be very big, that means I will need less power from the utility company to generate, to provide an electrical source to my refrigerator, for example. So I need, when I select an appliance, I need to look at the power factor of the appliance. I will go for the 0.95, 0.96 power factor, meaning that the reactive elements in the motor and in the other electronics that it's in my refrigerator, for example, will be minimized to assure 0.98, almost close to 1 power factor, which means that the effective is very, very close to the apparent. Now, the benefits of high power factor for the electric power utility is basically energy saving, because the customers have, what they want is effective power, real resistive power, ideally. They have to generate only that. If they, while generating the electricity, make sure that their power factor in the power station will be very, very high, close to 1. So they will need to generate only the power that will go to the load, which are the customers, and nothing will go back. So it's energy saving. Just like we said before, reduce transmission and transformer losses. Only one way, doesn't come back. Improve voltage regulations. Only one way, it doesn't come back. When it comes back, that means there's the voltage regulation is varied. There are fluctuations because voltage is being built on components and systems, and it takes time for the voltage to relax, to go down to 0 before the other one comes. So if every time there's a voltage in plus minus and it's getting ahead with a voltage minus plus, that means there's a gain between the two voltages on the different polarities. That means that the first one did not get to a resting while the second one came and start influencing it. So there's a voltage regulation point of a problem. An increase in available capacity throughout the power company without additional investment in generation or distribution. Again, if everything goes one way, most of it is basically available. The capacity will be available to the maximum. And in peak current demand, this is extremely important parameter. In peak current demand, we can actually, because we generate real effective 100%, theoretically speaking, 100% efficiency power, output power, that means even in peak demands of the market, there will not be a need to build an additional power station to supply the demand. Eventually, at the end, in the future, there will be another power station being produced, being generated, being built, but it postpones that particular investment. And again, just to summarize the formulas of active and reactive calculation, we went all to the top third of the picture. We went through this. This is the pure, true power. And we see that the power is I squared times R, and it's being dissipated by means of heat. The energy, the electrical energy, is converted to heat and dissipated to air, as we mentioned before. And then we have the reactive power, is I squared times the impedance. X is the impedance, which is a combination of the resistance and inductance and capacitance. And the apparent power is, again, the I squared times the total impedance combination of all the three measured in volt and amps. So this is a set of equations to present the three elements of the power: purely active, purely reactive, and a combination of the upper two.